Hello everybody. It's a pleasure to be here this evening to talk to effectively a computer screen who I hope is connected to the internet to somewhere between 0 and 1 million people to discuss the topic of steel plate shear walls. And so first thing to mention it right at the beginning is that none of what I'm presenting today would have been possible without the hard work of many graduate students with whom I've been working on this topic and who are listed here. And of course, the sponsors of this research, which are also listed and are numerous as well. So I'm grateful for all of that. And now let's move on to the presentation for this evening. So I'll essentially give a few examples of steel plate shear wall implementations, describe the fundamental behavior of the system, and then touch on a few topics like the significance of preventing in-span hinging in these walls, the implication of balanced design, post-earthquake replaceability of the web plates, and the two special systems of perforated steel plate shear wall and self-centering steel plate shear walls. A lot of the information on steel plate shear wall is available in an AISC design guide. The design guide was published in 2006, and there's been a lot of changes to AISC specification and even CSA for that matter in the 10, 15 years since. So it's a little bit dated, and AISC is in the process of, well, we're working trying to get the second edition of that guide out sometime in the near future. A lot of the topics a lot of the things that have changed since the original guide somehow are covered in the Ductile Design of Steel Structures textbook. Even though it came out in 2011, we had a pretty good idea of what would be in the 2016 edition of AISC, and the document is still pretty much up to date in that respect. There's only going to be one change in 2022, and I'll describe what that is as part of this presentation here. So a lot of these topics I'll discuss are also described at great length in the textbook. So what's a steel plate shear wall? In a nutshell, if you look at a frame which consists of beams and columns, and you infill the space between the beams and the columns with a solid steel plate, well, there you are. You have created a steel plate shear wall. There's, of course, a bit more than that, but that's, in essence, the concept by itself. Depending on which code you look at, the columns will be called either columns or vertical boundary elements. The beams are beams or horizontal boundary elements. And the plate is either an infill or a web, just different words to say the same thing. Now, they've been around for a while. For example, this is a picture from 1978 of a hotel in Dallas. And so there were instances where these walls were the more cost-effective solution, depending on specific applications, but they were rare and few in between because a lot of the times these walls were designed in a manner to prevent shear buckling of the panels, and that made them a little bit less competitive, I would say, than what we do nowadays. And nowadays, what we do is we make sure we use these infill plates without any stiffeners. So that means we allow them to essentially buckle and develop diagonal tension field action. And this is as an outcome of a study that was done in the 1980s at the University of Alberta by Geoff Kulak and others. And that's not a surprise then that we've seen a lot of more, in the early days, a lot more steel plate shear walls being built in Canada, like this one here, than elsewhere. But in no time, people caught up on the ID. For example, this is a steel plate shear wall in Mexico by Martinez Romero, who was essentially came across the Canadian code and saw the steel plate shear walls there and had just finished completing a tower with reinforced concrete wall and was building a twin tower next to it and decided to do it with steel plate shear walls for comparison purposes. So since then, they've been widely implemented across North America. This, to my knowledge, is the tallest steel plate shear wall building in North America. The building used to be called LA Live. It's a 56-story building in Los Angeles. And this is, to my knowledge, the shortest steel plate shear wall building. It's, well, it's residential construction on the high end. And you can see the numerous steel plate shear walls have been used in this particular case. Now, I'll let you guess where that particular steel plate shear wall is located. But I would say that at this time, there are, to my knowledge, steel plate shear walls built in the United States, in Canada, and Mexico, New Zealand, Japan, China, Costa Rica, and Guatemala. And if you have not guessed where this one is, it's actually in Costa Rica. It's a parking garage, and it's got a fair amount of steel plate shear walls in it. Now, some of you may know that in the 1970s, there was an earthquake in the San Fernando Valley, north of Los Angeles. And there's a hospital, the Olive View Hospital, which is pretty famous because it had opened just prior to the earthquake and had been built on the idea that flexible buildings are good, and because they take a smaller force from the earthquake due to the fact that their period is long. And there's a logic to that idea, but you have to have details that allow these large deformations to take place. And in reinforced concrete design in the 1970s, they were not quite there yet, as you can see on this picture. So this particular hospital had to be demolished because the damage was way too extensive to repair. And they decided that they would not get caught twice with the same problem of flexibility. And the new Olive View Medical Center was built using steel plate shear walls. The lower two levels were reinforced concrete walls, and the upper four levels were steel plate shear walls, and you can see the fabrication here in panels. Now, of course, I shouldn't say of course, but oddly enough, in 1994, almost at the same location in the San Fernando Valley, was another earthquake called the Northridge earthquake that tested this particular hospital. But it had pretty much been built like a tank. They didn't want any more damage in it, so it stayed elastic as a structure. The peak ground acceleration of the site was almost 1 G. The peak acceleration of the roof was 2.5 G. An amplification of 2.5 is typically what we see in buildings with a period of less than 0.5 seconds. So that's not a surprise by itself. But that example has often been cited, that building has been cited as an example for the need to provide adequate bracing to non-structural components. Because unfortunately, during that earthquake, the building was shut down again, not because of structural damage, but because of non-structural damage to sprinklers and other non-structural systems. But steel plate shear walls are very popular in hospitals because it is a very stiff structural system, which makes it easy to meet the tighter drift requirements imposed on hospitals. And at some point, engineers were wondering if it was only for new hospitals, because it's kind of hard to imagine walking inside a hospital with a big steel plate to retrofit an existing building. But an engineer, Jay Love here, sent me pictures of a retrofit of a hospital using steel plate shear walls. So now we know it can be done. Essentially, the way it behaves, if you know what is a tension-only brace frame, essentially it's very slender brace with KL over R greatly in excess of 200. So we can think there's an analogy here because the plates are very thin, and it could be similar to a tension-only brace system. Now, I don't want to spend time talking about a tension-only brace system at great length, but if you have a tension-only brace system and you cycle the building back and forth, when it's in tension, it yields, and as soon as you unload, you have a residual elongation of the member in tension, and then buckles the whole length and travels at the same time. So if you take two of those and you combine those two braces together, you get at the bottom the hysteretic loops that you can see there. And it means that at every time you want to dissipate the same amount of energy as in the previous cycle, you have to drift further and further onward. And that's an issue. It's one of the reasons why tension-only systems are not permitted by AISC. Tension-only systems are permitted by CSA within very tight specific limits of applications. So you might think that a steel plate shear wall is essentially a tension-only system with a bunch of braces that are essentially the plate that could be thought of as a series of tension-only braces. And there's some truth to that. You would need an anchor beam at the bottom to anchor those tension-only members. But by itself, it's not sufficient. So for better seismic performance, fully welded beam to column connection have to be added in the corner. so that the cyclic behavior of a steel plate shear wall is essentially the sum of the fuller striatic loops provided by the moment connections and the tension-only plates that dissipate a lot of energy, but sort of at progressively larger elongation. And the stiffness and the redundancy is typically provided by the infill plate. Now, once you appreciate that it's buckling and there's diagonal tension field action that develops in a steel plate shear wall, you might think that, oh, I know what to do with tension field action. We design plate girders all the time for tension field action. So maybe we could design a steel plate shear wall like a plate girder. Well, the behavior is similar to plate girders, but do not design steel plate shear wall following the plate girder specifications. There's too much, not enough time tonight to explain why it's not a good idea, but there's a whole paper that describes exactly that in great details. So to make a long story short, in a plate girder, you don't have the entire panel yielding and dissipating the energy that tends to be concentrated in bands. But here for capacity design, we need to take into account the entire yielding of the panel. And there's about 5 or 6 other reasons why we shouldn't do that. So here's a steel plate shear wall. You have the beams, the column, and the infill plate painted in white. We painted a grid of black lines to make it easier to follow yielding and buckling of the plate. The length divided by thickness ratio of that infill plate is close to 4,000 to give you an idea of slenderness. And here's a video to illustrate how this behaves. So we're pushing and pulling the top of the frame left and right. And in the elastic range, you get elastic buckling and the whole thing comes back into its original position. But we want to yield this thing, so we are going to progressively larger drifts in each direction. And at each cycle, when we do that, we yield the plate some more. So when we unload, the plate itself is longer than it used to be. So coming back to the 0 position, now we have a buckled plate in essentially both directions. And we have to drift further out and further out to yield some more. And you'll see that the amplitude of buckling keeps increasing as we further increase the drift. And of course, that gives you a good idea and a good picture as well of the direction of the diagonal tension field action that develops in these steel plate shear walls. We have gone to a very large drift with that specimen without being able to fracture the plate essentially. And we ran out of stroke to speak of. So here's the outcome. I think we had a little bit of damage at the corner of the weld when we ran out of stroke on the actuator. You can see the extent of the ductile response of that wall. And this wall is a little bit different than the one I described. We did not have moment connection. We only had clip angles on the web, but they were gigantic clip angles because the diagonal tension field action puts a very large actual force in that beam. And so we had to transfer that to the column. But if you take the hysteretic loops of these clip angles and take it out, you're left with the hysteretic loops at the bottom of the infill plate itself. And you can see that it does approximate the behavior of a tension field or tension-only brace, which is why we want these moment connections in the system. I don't plan to go into great details in mathematics. That's too late in the day for that. But just to say, once you appreciate that you have a diagonal tension field action, you can develop into a horizontal and vertical component as acting on the boundary elements, beams and columns. And normally what I do when I teach this, I flip my textbook 90 degrees and I show that this could be a column just as well as a beam. And if we resolve the equations of this uniformly distributed load at the bottom over the entire length of the beam, we get this equation right here. And the mathematics are actually quite simple and you could do it yourself. But what it says is that if you know the horizontal load applied at a level of the steel plate shear wall, let's call that F sub H, and you know the length between columns, L, and you know the angle alpha, let's say it's 45 degrees for now, so sine to alpha becomes 1, and you know the yield stress of the steel plate, you can pick the thickness of the plate immediately. So in a nutshell, you can design the plates at every level of a steel plate shear wall on the back of an envelope in no time. It used to be in Canada, there was an analogy that was done. They used to say, design it as a brace frame, and then once you have the area of the brace, you can use this equation to convert that into a thickness of a plate. Honestly, with the previous equation, I don't see why we would need to do that. You get the thickness directly. But once you have this thickness, you need to create a model, and here's one model that is called the strip model, by which you will be able to determine when the strip yield, what are the forces on the beams and columns surrounding the plate. Now that strip model was again part of this original study in the 1980s. It showed that using a very simple model like that, you can pretty much capture the stiffness and the backbone strength of a steel plate shear wall, which makes it convenient because you don't have to model the steel plate shear wall as a continuum. You can essentially use a bunch of small strips. And that's what engineers in practice typically do, as this example here that is for the retrofitted hospital I showed earlier. So, since we're speaking of the angle, in the specifications right now, there is this equation with a tangent to the fourth that was produced in the 1980s and that can be used to calculate the angle at every level in a steel plate shear wall. It's giving a sense of great accuracy and great precision, but in actuality, it's a little bit more complicated, as I'll show in a moment. And to simplify the work of engineers, the code says you can use 40 degree everywhere, and that should be fine, which sort of raises the question, if you can use 40 degree everywhere, why would you go to the trouble of calculating this complicated equation for a different value of alpha? The reality is there's no single angle at any point in time, even with the complicated equation. It's sort of a misleading equation in that sense. The angle will vary across the plate and as a function of drift and as a function of inelastic behavior. So here's a snapshot in time at 2% drift. The figure on the left shows you the principal stresses and all of the finite elements that were used to model the infill plate of that steel plate shear wall. And if we only look at the boundary itself, because there's too many arrows on the left, you can't see anything, you will see that the values of the angle vary over the entire length of the beam as well as over the entire length of the column. In reality, that snapshot is at 2% drift, but if we would have done a picture at any other drift, you would have got slightly other different values as well. And here are some curves that show how these values change as a function of drift for the top beam, the bottom beam, the left column, the web itself. And so the idea that there's a single angle at any point in time is not quite true. What is important, though, is to use an angle for design that will be safe to use. So if we compare the results from finite element analysis, so here's the AISC interaction equation that we would use to design the beams and the columns. Subscript F sub E means result from finite element analysis. Subscript CD means the strength of the member. So if you do your interaction equation with the results from finite element analysis, and you divide that by the results you would get if you did an analysis using strip at a specified angle alpha, if this is less than 1, it means that the reality finite element is less than what you calculate with a constant angle in your strip model, therefore you are safe. And what we find is that 45 degree or 40 degree doesn't make that big of a difference. In fact, either could be used for design. And honestly, if I'm going to model strips in a frame, it's going to be a lot easier for me to do it with 45 degree story to story than to use any other angle. So it's nice to know that 45 degree can work. And so here's an example comparing this ratio on the blue line here for 40 degree and on the other blue line here for 45 degree. You can tell 0.91, 0.91. There's not much of a difference between the two, and they're all pretty much less than 1, and that's all we need to know. So that's what I said, why I said earlier that the angle alpha, permitting the use of 45 degree over the entire height, is a nice upcoming change in new provisions for seismic design of steel plate shear walls. Now, a couple of topics. The codes say we should not allow in-span plastic hinging in the walls. So why is that? Why does it matter? We can have a plastic hinge at the left and right end of the beam. It's sort of unescapable because if we do a plastic mechanism and we push on this plate and it yields in shear and essentially diagonal tension, expression of shear, we will have a parallelogram that looks like this and some bending in the beams resulting from that pull from the plates that will produce hinging at the ends of the beam. So the maximum strength that is in the first blue circle on the left is what I showed earlier when we integrated along the length of the wall the pull from the plate. And the additional circle on the right shows the additional strength provided by those 4 plastic hinges. And if we had multi-story buildings, we could write similar equations to find out the base shear strength of the walls. That's the type of mechanism we want. These beams will develop plastic hinging at their end. Why then, how do we get from that mechanism, which has plates yielding everywhere, the forces in the beams and the columns? We essentially do free body diagrams considering the shear, axial force, and moments at the ends of the beam. So having these free body diagram, we can calculate moment and axial forces in the columns, for example, like here. And this kind of free body diagram here will match perfectly what you would get from a pushover analysis, and this is good to know. Earlier methods that had been proposed to calculate forces in columns do not work quite as well in terms of providing accuracy. And why is it important to get a good estimate of the forces in the column? Well, the plastic mechanisms that we rely upon, which is diagonal tension field action in the plates and plastic hingings at the end of the beams, will not happen if we start to buckle our columns, for example, and that would lead to an undesirable behavior. So once we have these free body diagrams on the columns and the beams, for example, on the beam, you would have a pull coming from the vertical component of the yielding plate above and a pull coming from the plate below. That gives you 2 different vertical forces. You can resolve the resultant. That gives you a UDL on the beam. That UDL, if the beam was pin-pin, would give you the moment diagram that you see with the black line right here. So if we want to have plastic hinging at the ends only, we cannot have this maximum moment here. If the ends of the beam were able to resist omega L squared over 8, we would get the red line right here. There would still be a plastic hinge somewhere along the length. To get the hinge to be at the end, we need to design that beam for omega L squared over 4. And that's a lot. I'll show you a way to get out of trouble. You could essentially use a technique to reduce the strength of the beam right here so that it would yield here before it actually reached the strength of the beam right there. And so that's why in this presentation tonight, you'll see some beams that have been, the flanges have been trimmed essentially to use what is called reduced beam section detailing in the beams. So, but in the meantime, let's focus on what happens if there is in-span hinging in the horizontal boundary element. And if we design instead of that, something for omega L squared over 4. So, and this is the optional alternative that I'll come back and show some examples of that later on. So what we did is we designed a beam, we designed a steel plate shear wall, not paying any attention as to where the hinges would be. And then we designed one on the right where we designed the beam for omega L squared over 4, which will force the plastic hinging to be at the ends of the beam. And then we compare the behavior. First thing first, you don't get quite the same plastic mechanism. For example, if you resolve what is the strength of that system, which will have a plastic hinge that's not at the end, but somewhere in span, in this particular case, we had about 15% less strength. And you might say, wow, that's not a big deal. I can live with a wall that has 15% less strength. And okay, that's acceptable if you say so. So then what we did is we did a cyclic analysis, pushing the wall back and forth to progressively larger displacements. And we compared the behavior of both walls. When we designed the beam for omega L squared over 4, the vertical displacement of the beam, residual vertical displacement, did not grow too much, half an inch, but in the other one, we had up to 2 inches of vertical displacement in the beam. So it means that after the earthquake, because your plastic hinge will push the beam down in both directions, it will keep accumulating and you'll be left with a larger deflection in the beam. And you might say, I don't care, it's just a beam that will have to be replaced anyhow, and that's okay if you say so. So the third thing that will happen, though, I don't think we can close an eye on it. And the reason is that if we compare the hysteretic behavior at the ends of the beam, when we cycle that frame back and forth, we see that, and that was quite a surprise when we saw that, we didn't quite expect it, that the plastic rotations tend to accumulate always in the same direction. That's a consequence of the pull of the plates, and so it's not quite a moment frame action, which would give you hysteretic loops. And so once one goes through the time history and traces that, it is logical. but it's kind of hard to explain in a few minutes, but it does happen. So if we have a steel plate shear wall that will go, say, to 3% drift, and that value of 1 here means 1 times 3% drift, the actual inelastic demand on the connection is about centered here. It's like you're cycling it at plus or minus 1.5% drift, which is something most connections can take. And that's why steel plate shear walls are not required to have special ductile moment resisting frame type of connections. The regular moment connections are satisfactory. But if you do not design that beam to be sized for omega L squared over 4, and therefore you allow plastic hinging in the middle to form, we get this great increase in the rotation demands on the beam. We essentially get the equivalent of plus or minus 3% or 0.03 radian. So it's like 0.06 total divided by 2. And I don't think an ordinary connection can resist that. And in fact, we've built a wall in the lab that exactly was like that. And it, of course, could not resist this kind of inelastic demand, and the connections fractured. So that, to me, is the main reason why we should not allow plastic hinging in the middle of a beam in a steel plate shear wall. The second issue I want to talk about briefly is the implication of balanced design, because naturally, as soon as you realize that the plastic mechanism for a steel plate shear wall consists of both the infill itself and the plastic hinges at the end, the question is, can we split our lateral load somehow between the two? And if you look at the design guide that we did in 2006, we thought, well, why not? I don't know why. So why we couldn't. So we assumed the value is, I think we split 25% in the columns and 75% in the plate. But that sort of got looked into afterwards, and we realized that, well, it's not quite that clear. And let me show you why. So if you have a force applied at a level, and we'll call that V sub U, and you say my plate will have to resist that force, and whatever else I have afterwards, 4 MP over H, that's gravy. That's a little extra that we'll have, that we're happy to have, but we won't design taking it into account. The other approach is you say, no, I'll take everything and I'll divide somehow between the column and the infill plate, and we'll make it work. What's the consequence of that? And I said in 2006, we divided 75-25, but really we could take any percentage of the force and say that goes in the plate and the rest goes into the column. So that percentage would be kappa. So whatever force is applied to the story, you'll say, I'll take kappa, say 75%, design my plate to resist this, and the rest goes into the columns. So if you do that, this is a figure that shows what happens when kappa varies from 0 to 1. So if kappa is 1, it means you design the plate to resist everything. So you get your design strength over the design force, a plastic strength over design force, that's a value of 1, and you get that extra gravy coming from the plastic hinges. And that extra oomph that you get there will depend on the aspect ratio of the wall. And so when we said 75-25, we had no clue. But in reality, if you want to be really fancy, you can find this balance point right here that will change from the aspect ratio, where at this very point, when you do capacity design on the rest of the surrounding frame with the plates pulling on the frame, it will give you a frame that is exactly the strength you need to resist its share of the load. So it's kind of a neat point. We'll call it the balance point. And the question is, if we design for the balance point, technically, we should save steel because we do not have that extra strength in the system, and therefore it would be an optimal design. The catch is you can't fool Mother Nature, of course. If you put less material, something is a trade-off. And so, what is a trade-off? What we did is we used the FEMA P695 methodology that is well known in the United States to calculate the R factor that we should use for design. I don't want to spend too much time on it because it's a tedious methodology to use. Essentially, what we did is we did a design for the balance point and a design for the plate takes 100% of the load. So when you take 100% of the load for the plate, they both have the same design force, but the point that is balanced here has a little bit more strength because of the phi factor, but that's about it. Whereas the other one has all of these extra strengths coming from the plastic hinge that we get, but we don't account for it when we design the thickness of the steel plate. And so comparing the behavior of these two designs, we built finite element analyses for the system, for the walls, taking into account P delta effects, the whole thing, leaning columns. We developed nonlinear models that can capture when the plate degrades and when the columns and beam degrades through cyclic testing. And I always look at this slide, which we can talk about it for 15 seconds, but it took 6 months to get that curve here and to calibrate it to 33 tests that were previously done on steel plate shear walls. So it looks simple, but it took an awful lot of time to get. And then we run these nonlinear analyses to see what happens. And so the vertical axis is the intensity of the earthquake. So we run an earthquake, see what the response is in terms of interstory drift on the horizontal axis. Take the same earthquakes, make it a little bigger, a little bit bigger, a little bit bigger. So if you follow a curve, you're essentially following an earthquake, and you get to a point where the earthquake is so large that the drifts increase in an unbounded manner, which means collapse. It's an instability for the system. And the FEMA P695 methodology makes us use 44 ground motions. And we compare the behavior of these two walls. Both walls were designed for the lower line right here, 1.5 G. And of course, the wall that is balanced as a lower margin, if you want, between the average response and the design value. And the walls, the other wall is a slightly larger margin of collapse. And so the question is, what is an acceptable margin of collapse? And the methodology FEMA P695 tells you, well, the margin should be some number that you will adjust. And there's a whole series of parameters you have to take into account to adjust the margin. And then it tells you, according to current practice, we structural engineers think the collapse margin should be X. Did you meet that margin or not? And for the wall that where the plate was designed to take the entire load, it met the criteria, and it's okay. And for the other wall that we thought we were really clever by balancing the load perfectly between the columns and the plate, it did not pass. And in fact, I think for this particular wall to make it pass, we would have had to reduce the R factor in the US code from 7 to 5.5, but then you would get a different R factor depending on aspect ratios of the wall, which makes it unmanageable. So it's therefore not desirable because first of all, we couldn't prove that it would work. But second, there's an easier way to show that it's not desirable, and it's this figure right here. For the wall in which we designed the plate to resist the entire horizontal load, these are fragility curves. Essentially, to make a long story short, the fragility curve tells you from all of these computer analyses what would be the, for each curve, for example, the probability of getting 2% drift. And the probability of getting 2% drift is 50%. What about 3% drift? Well, we have a 80% chance, I guess, 2% probability of exceeding 3% drift. So if we look at the wall where we had balanced everything, we have a 20% chance that really we could get drifts as large as 7%. I don't think that is sustainable. I don't think a building can get 7% drift without having extensive damage. Its cladding would probably be all in the street. So right there is, I think, a good message that we probably should not, for the time being, distribute the load between the plates and the columns and design the plate to resist the totality of the load, which is A, good, and B, easy to do because it's a single equation. You can pick the thickness of the plate at every level with a one-liner. If you really want to save save money on saving material, and you have a relatively low-rise steel plate shear wall, a much better solution is to use a perforated steel plate shear wall. Perforated steel plate shear walls sort of came about when we were looking at low-rise buildings, and we thought, sometimes you want to use hot rolled steel, but you hit the minimum thickness available. And having a wall that has the same thickness over the entire height is not very good because you know that the energy dissipation will concentrate at the lower story, and that will create larger drifts in the inelastic response only in one story as opposed to distributing it over the entire height. So we, at the time, had a bunch of solutions using light gauge cold steel. Yes, you can do that. You could also use low yield steel, but that's not a product available in North America right now. It's a steel that yields at 15 KSI. So that would be what, 100 and something, 115 MPa, I think. So it's not available here, and it has a tremendous amount of strain hardening, doesn't have a plateau, so it's kind of hard to use it for design in that application here. And the third approach is really the easiest, is to use a perforated steel plate shear wall. So you essentially accept that you'll have diagonal tension field action at 45 degree, and you essentially, by using these holes, it's like eliminating some strips, essentially, if you think of it. And here's an example of a perforated steel plate shear wall that was tested. This was done in collaboration with my good friend Casey Tsai at Encre in Taiwan. Usually we paint our specimen white. This one got painted yellow for reasons I can't remember, but because of the holes and the color, I fondly refer to it as the Swiss cheese wall. And so you can see the lines painted at 45 degree that indicate the direction of the tension field action. And somebody asked me once, can we make the angle something else than 45 degree? And I said, if you can figure out how to line up holes in two directions with a different angle, be my guest, you can. So right now, let's stick with the 45 degree. These walls perform just as well as the regular walls, and we were able to reduce the strength compared to what we would have got for a comparable solid plate. So this is essentially, in a nutshell, what a perforated steel plate shear wall looks like. If we take a typical strip of the wall, like you see here, we do a finite element analysis meshing of that. And because of symmetry and all kinds of things, we can mesh actually just a quarter of it. And we pull on that plate to see how it behaves. That should give us some indication of how the many plates on the wall would also behave. And what you can see here is that yielding actually spreads over a large part of the plate. It's not just concentrated next to the hole, but it spreads because of strain hardening and a few other things. And so when we compare that to the behavior in an actual wall, we can see that indeed, if you follow the light blue and green lines here, you have strips that yield, maybe not uniformly, there's ups and downs, but it does yield enough to provide you the drift that you need to resist the seismic forces. In fact, if we compare the total uniform strip elongation that we get, say, from the unit strips, which are the solid lines, and steel plate shear wall, which are the points, there's fewer of them because it takes much longer to do the finite element analysis of a complete wall than just a single strip. They're close to each other. They would be exactly on top of each other if the beams would be infinitely stiff and the columns would be infinitely stiff. The difference is due to the deformations of the beam, essentially. So it's not bad. And if we look at what would be, say, if you look at this line right here, this black line means at what elongation of the strip do you get somewhere in that strip one finite element that reaches 20% elongation. That would be the situation. So for example, if you look at the diameter of the hole divided by the distance between two strips of 0.5, you would reach a 30%, a 20% strain somewhere in that wall when the total uniform strip elongation is 3%. And so if you convert that into a frame drift as a function of total shear strength, when you get that 20% somewhere, and usually it's only at one location next to a hole, or many holes, but it's not the entire strip that reached 20%, you have more than 3% drift. And most steel plate shear walls will not exceed drifts of 3%. So the perforated system works. There's an equation in the code that indicate what is the strength of a perforated wall. Intuitively, you would think if I remove half the area, I lose half the strength, but it's actually because of strain hardening. It's a little bit better than, it's not as big a reduction as you would like. So you have to bit of a calibration factor here that is based on experimental results and finite element analysis results. But that's where this equation comes from in the codes and standards. So these walls are handy. And particularly helpful for low-rise buildings. Here's an example in Montreal. There's a few of those in Montreal that I'm aware of. And what you'll notice here is that if you look at the connections at the end, they have used the reduced beam section such that they don't have to design the beams for omega L square over 4. They can optimize the beam sizes as well. So it's pretty clever there to combine that with the perforated system. I think you're getting to quite an economical level at that point. This is an implementation of a perforated steel plate shear wall in New Zealand. I believe it's a 3-story building. I think there's about 4 more on the drawing board there. And here's a perforated steel plate shear wall, at least for the upper stories, as you can see here in Los Angeles. So it's a system that is gaining in popularity, apparently. If you want to run things through the holes, that can be pretty handy, but they're not necessarily at the best location for running pipes that tend to be under the floors. So sometimes there's another option that you can use to accommodate the passage of utilities through an infill plate without significantly, in this case, reducing the strength. You would have zero reduction in the strength in that particular case. It's to reinforce the corner with an arch. And so that gives you a nice big hole through which you can run utilities, and the diagonal tension field action effect has to essentially be transferred through that arch. And there's two things that will happen in terms of the point load that you get right on the beam and the column. First, there's a pull from the plate that's going to come up as a tension force right here. And then as the angle closes in the corner, there's a pinching effect that will give you a compression force. So those two forces sort of act at the same time, and the code provides equation for what these are for this particular case. And here's an example of an implementation of these cutout corners in the same building in Los Angeles that I showed earlier, but at the levels where the plates were solid. The question I often get is, can we replace the plate after an earthquake? And the answer is yes. And so again, this was proven as part of a joint project with my colleague again in Taiwan, Casey Tsai. That project had 3 phases: to run the wall, a full-scale 2-story wall, through an earthquake that has a 2% chance of probability in 50 years, meaning a return period of 2,500 years. Then cut the plates, replace them with new ones, and repeat the severity, the same severe earthquake. And if the wall is not failed yet, let's continue to cycle it to failure. So here's an example. This is a full-scale specimen with full-scale technicians replacing the full-scale plates. And they're in the process of placing the plates after the first pseudodynamic test that damaged the plates. They're putting brand new ones right here. This is the second pseudodynamic test where we are replicating the displacements that the wall would see during that earthquake. So it's I think 25 seconds or strong shaking there or something like that. Just showing an example, a sample of it. You can see the plates buckle. This is the state of damage after the pseudodynamic test. This earthquake is over. The maximum peak drift that were reached at the lower story were 2.6%, and at the upper story were 2.3%. So the wall is still good. So let's keep cycling until something breaks. So first, you'll see that there's a little bit less stiffness at the beginning because the plates are sort of flopping around. They have to go back to their largest previous displacement to start yielding again and pick up more strength. So what will happen is that about 3% drift, you'll see one of the level where the plate is, the weld of the plate to the boundary frame is starting to fail, and the strength will drop, and that's at the base level right here. But because this is a displacement controlled test, we can keep pushing and still test the top level. And this is what we did in this particular case. And we reached a drift of 5% at the top level before we had to stop because we could not transfer the load anymore. The flooring system had failed. We could not transfer the loads to the wall at that point. So I'm not saying you should expect to squeeze 5% out of your walls, but at least being able to go to 3% is already very good. And this at the first level, you can see the amount of the weld that sort of fractured along this entire wall. And surprisingly, in spite of this amount of weld fracture, the wall was still resisting about 50% of its previous strength before the failure. Another question I sometimes get is people say, well, there's going to be a residual drift after an earthquake, and so what do we do about that? Well, that's not unique to steel plate shear walls, by the way. It's probably unique to almost every structural system that is in the seismic design specification, whether it's NBCC or ASCE. But if you really, really don't want any residual drift, you've got to take some special detailing approaches to achieve that, and that's called the self-centering steel plate shear wall. You may have seen some of that work on self-centering moment resisting frames, where essentially the beam has a post-tension cable going all the way across, and there's no physical connection other than contact between the, as far as flexure is concerned, between the beams and the columns. There's some shear transfer mechanism, of course, for the web, but the beam is free to rock and open up essentially from the face of the column. When it does open up, the post-tension elongates, and therefore it wants to close the gap. And as soon as the earthquake is over, it tries to bring back the structure to its original position. So we can do the same thing in a steel plate shear wall. We can prove that it works on a computer model. The red line in the historetic loops would show that it's a rigid beam behavior, and the blue lines flexible beam behavior. But you can see, at least in principle, if we do that with tension-only members, it would come back to the zero position when the forces are removed and the earthquake is over. So here's what a detail like that would look like. You can see your steel plates are here. We've painted the grid on the steel plate as always, so we can see where it buckles. We had to cut open the corner, because if you allow the beam to open at the column and the steel plate goes all the way to the corner, you're going to rip open that steel plate. So you have to sort of detail that cutout here, and there's some equations that we've developed to allow it to take a reasonable amount of strain without unnecessary impact on the wall. And then this is a function essentially of the radius that you cut. And we've, I don't want to go into the details. I just want to bring it to your attention that it's a detail that has to be there, of course, if you're going to allow the corners to open and rock like that. But there's a detail that there's a consequence of allowing a frame to rock that is going to be there, whether it's a steel plate shear wall or a moment resisting frame, and it's called beam growth. If you have a point of contact at the top of the beam on the left of the first level beam, and at the bottom of the beam on the right point of the first level beam, and these columns are infinitely rigid, at the second level, the column is going to pull away from the beam. So it's a bit of an issue. It's been brought up by many people. It's called beam growth. So far, our own rocking system here, our own self-centering system, we decided to bevel the beams and only touch with the flange. And if we do that, there is no beam growth. Now, because there's no beam growth, you cannot run your post-tensioning from column to column, because the column are at the same distance from each other all the time. But you can run them from column to some anchor point along the length of the beam, and that will do the job. It will recenter everything. So that's essentially what a detail looks like that. You've got exactly what I mentioned, touching at the column, the post-tensioning going to anchor somewhere along the length of the beam. This is what you see here in the lab, this actual implementation of the detail. And we built a 3-story steel plate shear wall with that kind of connection. We added some masses to it because we wanted to put this on the shake table. So the masses are essentially connecting to the beam to transfer the inertia forces from the floors to the wall. Before putting that on the shake table, we want to try it out pushing from the wall in case something goes wrong. We can see it there, and it's not going to be as fast as on the shake table. We can see it in slow time. We have to allow motion at the bottom. We don't want to do plastic hinging in the column. So there's a couple of ways to do it. This is one of them. There's another one I'll show you later on. And then we did cycle back and forth from the reaction wall to make sure things would happen as intended. And it behaved pretty much that way. So we're quite pleased with the outcome. And this is too global. You can't see anything. So I want to show you a close-up view of the plate. So that's yielding as it normally does in a steel plate shear wall. But more interestingly, in the corner here, you can see the bottom flange is going further away and closer to the column flange, bottom flange of the beam. You can see the slotted hole connection for the web, where it allows this rocking movement, and it worked as intended in this particular case. Good. So we're happy, and we move on to look at what the hysteretic curves look like, and we say, whoops. How come it's not coming back to zero? This thing was supposed to come back to zero, right? That's because in the corners, you have a little bit of a concentrated force in compression. The length, K/R, is not very large in the corner. So even though the plate is thin, you can get a little bit of compression. There's if you want to bring this to 0, you can increase the post-tensioning force, and that would do that. But I'll show you in a moment, we don't even need to worry about it. To show that it's really happening because of the corner effect, we designed a steel plate shear wall, like the one shown on the right, that looks exactly like the one in your computer model, essentially a bunch of strips, right? That can only be in tension. They have to be, in our case, in both directions so that we can model the change of the, if you push to the right and you push to the left during the earthquake, the diagonal tension field action change direction. So we're going to jump here in the middle of the test. And you can see at that point that the strips are completely buckled until they go in tension again, and they yield and stretch some more. Why are they buckled so much? It's because we tested this building to 9% drift and nothing failed. And then we got scared because have you ever seen a building at 9% drift? We didn't want the whole thing to collapse in our lab. So we figured this thing probably would go all the way to 20% elongation. It's like testing a bunch of tension coupons, right? So it's not a concern there. So we continued. Whoops. Next slide. Echo. So I think that's it. So moving from there, we look at the hysteretic result we got from those strips, and there, sure enough, it comes back to 0, right? So should we do something? Should we design all of our walls like a bunch of strips? Well, you could, but we decided to go and do it as a two ways, a two-step process. One is a pseudodynamic full scale, and one is a shake table test, and see if it made a difference. So this is the full story, two-story full-scale test in Taiwan again, where we did a pseudodynamic loading. It's a collaborative project with many universities. Here's our full-scale wall. Here's our full-scale graduate student. And in this case, you can see the anchoring of the post-tensioning bar inside the beam to achieve the recentering effect. You can see the beveling of the beam. Everything is the same, except the only difference is at the bottom, we post-tension the column as opposed to use a pin. So if you look at this detail, the column at the first floor has a little platform. There's a post-tensioning bar going into the base, and this column is just essentially flat there. There's a few guiding system, by the way. You don't want the column to walk away on its own and start to wander around in the lab. So we have to make sure it comes back on its own footprint. But other than that, it's free to rock because it's anchored at those locations. So let's see. So here's a pseudodynamic test. Whoops, I got to go here. So here's a pseudodynamic test where we again displace the wall to where it's supposed to go during the earthquake excitation. You can see the cutout corners again. A little bit hard to see the opening at the bottom of the flange because there's too much instrumentation there, but it's happening as expected. And if you go to the base of the column and you look at the rocking motion in that particular case, it again performed as intended. Rocking behavior, and in this particular case, well, it's an alternative to your base column detail, essentially. So the problem with these full-scale specimens is it takes an army of people to look at the results afterwards. And so here are a large number of graduate students climbing on the wall to take measurements of the buckled shape and the length of the weld failure. This wall was tested to 4% drift before we saw significant failure of the welds connecting the plates to the boundary frame. And eventually, once it started at 4%, at 4.5% drift, we failed the entire plate, the entire weld connecting to the boundary frame. Then we did the shake table test. So we came back to scale in our lab and used an earthquake that matches perfectly the design spectra. In other words, what if you're lucky and the earthquake that happens match perfectly your design level for the wall? So there's no unfortunate understrength or fortunate overstrength. You're right on the button. So we ran ground motions starting at 10% of the design basis, 25, 50, 75, 100, 140 times the design basis, and then an aftershock at 50%. So here's the test on the shake table. Watching a steel plate shear wall front on like this is not particularly useful because you see the whole building move, but you don't see the plate buckle very cleanly. So I'm going to not spend too much time here and go straight on the other movie, which is at an angle. looking at the plate there. And this one is at 140% the design level. You can see the buckling taking place. Nothing exceptional here to report. No failures happened in that particular plate during that particular ground motion. Now, the question was not, can it survive an earthquake? We knew that. But we wanted to know, will it recenter, right? Or are we going to be stuck with a residual drift? So let's take a look at the history itself. The time history response of displacement of the wall at 140% design basis earthquake here. And you can see that it comes back pretty much to zero. In terms of drift, it's less than about, that was it, 0.1% drift. I would call that pretty plumb. And so what's happening really is, even though you have a corner that's a little bit in tension, and when we were doing cyclic, we're going to a larger displacement and a larger displacement. And so we're always stretching the plate and compressing it right afterwards. In an earthquake, there are all of these little cycles that come up at the end and tend to shake it back into original position and fight that little compression, diagonal tension, and do it successfully to bring things back to plumb. What you need to know, though, is if we look at the maximum absolute root drift as a function of the base shear that we reached during the earthquake, we ran the 140% twice, and you can see the second time we run 140%, we drift a little bit more because the infill plates have stretched, right? So you don't start with a virgin specimen. In fact, if you got rid of all of these tests before and you did 140% flat on first test, it probably would have a smaller drift than what we got here. And when you do the aftershock at 50%, again, because the plates have stretched before, you're at a larger drift than the first time you hit 50%. So that's sort of a consequence of having a plate that yields and a moment frame action. I'm going to show you this video because we figured, what the heck, we did the strips along the wall, let's put it on the shake table. But we forgot to tell the shake table operator that this one has half the area in the infill plate that the other one has, because we essentially have half of the area to resist. We took a bunch of it to create those plates. So we ran at what we thought was 100% the design level, but in reality, that's 200% the design level for this particular structure. So we're fortunate that it's quite ductile and nothing bad happened. So to conclude, we've seen an increase in steel plate shear wall construction since the 1990s. The recent research has certainly enhanced the understanding of the seismic behavior of steel plate shear wall in the past 15 years. We now have enhanced free body diagrams for capacity design for these boundary elements. We have a better understanding of the flexibility factor, and these are two things I didn't talk about today for lack of time. We understand that in-span hinging has consequences. We understand that balanced design is maybe not a good idea, and it has consequences too. We understand we can post-earthquake replace the plates, and we can also have a more resilient system if we want to invest in extra stuff to make it self-center after the earthquake. So now, I have no idea how many people are here, and I was trying to think, how do I know if I'm talking to an empty room through a computer screen or a million people? So I came up with this little idea. Maybe it's good, maybe it's bad, but I said, I'll do a giveaway essentially, to figure out how many people are still awake at the end of the seminar. And so if you want to participate in the giveaway, just forward me an email and put subject giveaway. And so if I receive X email, if X is 10, for example, before 10 p.m. tonight, the winner is 10/2, a fifth email I will have received in my mailbox. I presume I won't get 1 million, so that should be manageable. And what do you win? Well, it's not the gold mine here. So I figure I'm going to give one of the two ebooks shown on the left. It's a shame I don't have the one on the right as an ebook, because it's about an earthquake in Montreal 2 weeks before a referendum on secession. So that's making it sort of interesting for a Canadian audience, I guess. But you can check whatever you want on the website there and see if there's one of the two you prefer, you can indicate. And of course, feel free to send me an email. And if you don't want any of those books, that's fine, just say hello. And so this way I'll receive a bunch of emails and I'll get a sense of who was there, which is always nice to know. If I give a presentation in person, I get to see you, I get to talk to you, we share a glass of wine. So WebEx is none of the above. And so I was trying to get some way to connect with people and know who was there tonight. And so I hope you've enjoyed that. And from what I understand in the format of this webinar, we're going to have now a question period. So Alex, back to you.
Yeah, thank you, Michel. It's a very exciting presentation, an insightful presentation. So now we are in the Q&A session. So we got some question. If you look at the chat, we got some question. So Michel, why not just start the first question?
Okay, let me check the chat. Let's see. Oh, there's a lot of questions. Okay. How does elastic shortening of the boundary columns and gravity load deflection of the beam affect buckling of the steel plate? That's elastic shortening. So I presume this is for gravity during construction. Tibor, you're asking that question. Hi to see you, Tibor. Always nice to have you around. There's different philosophies there. Some engineers say that really you shouldn't worry about it. It's just going to compress a little bit your plate. And when you're going to be in transverse motion mode, you're going to still develop diagonal tension field action. Other engineers have done their projects where they have started by welding the plate, and at some point they come back and grind the weld out and re-weld it to get rid of that little deflection. So it's a matter of preference, really. I think there's no standard approach. I don't know if that answers your question, Tibor.
Yeah, it does. It's basically an issue of strain compatibility. You load these columns and it's connected to the plate, and when do they, how much of the capacity you use up of this plate that's supposed to take lateral load, but you're using it up now for gravity load.
Right.
And the beams will deflect. So the beams may deflect, I don't know, 10 millimeters. So now your plates are squeezed as well. So it's not that simple as it looks as I see it, but I never designed one.
Right. So I think for some projects that I'm aware of, they essentially remove the weld at the bottom. You can sort of, it's a square. You don't have to remove all four sides. You can do it with three sides and then re-weld it back to make it flat again, so that you have a final flat plate when you start back. Let's see, what else? What are current research needs or things that still need to be addressed and studied in the case of the inclination angle in solid plates? I think solid plates is done. I don't think there's anything else that I would see as a need to study. The 45 degree there, it took a lot of work to get there. The 45 degree, I think, was first proposed by Jeff Berman at University of Washington. And a lot of people thought it was very good, and there's an attraction to the 45 degree if you're going to do modeling, right? But I think there was some hesitation because it was done on a 1-to-1 aspect ratio single-story panel. Even though it was a very well done piece of work, it was analytical as well as experimental. There was some concerns that it was not guaranteed that it would work for everything, right? So we spent a lot of time trying multi-story buildings, different aspect ratios, and things of that nature to be able to validate the 45 degree that had been proposed by Jeff Berman. And everything we did sort of confirmed that it's a good compromise. And the reason I say a good compromise is because the angle change all the time, right? So there's no single angle at any point in time, but if you can pick an angle that gives you a decent design that works and that's safe, you're happy. And it turns out the 45 degree works. And I'm thinking, why would I want a different angle? It's perfect for modeling in SAP, or in any computer program. It's an easy one to deal with. So personally, I think it's done. Somebody else may have a better idea. I don't think I know everything, but if I was to try to do another project on the angle, I wouldn't know where to go. I think we're there. So thanks for your question, Vahid. Does it answer it?
Yes, I was actually on your explanation. I was actually looking at your one of your papers that you published on 2019. It is called Complementary Evaluation of Diagonal Tension Field Inclination Angles. And in there, you mentioned that future research could investigate the sensitivity of the inclination angle in case of taller SPSWs or the other geometries. Just wanted to know that if they are that important to investigate and
well, the reason we said that is because we stopped at 3-story, right?
yes.
So every time you do a study or you publish something, you want to acknowledge your boundary conditions, your assumptions, right? The limit of your knowledge. And the limit of our knowledge, well, if I think about it, we only did 3 stories. So if somebody wanted to demonstrate that we were wrong and wanted to go through the trouble of doing, I don't know, 10 stories, 20 stories, 30 stories, and demonstrate that at some point it's not true anymore, yeah, that would be interesting. But I wouldn't be the one doing it. I think there might be a marginal return at that point.
Thank you, sir.
Yep. Let's see, other questions. High-rise project. Yes, has steel plate shear wall system been used in high-rise projects in the 40+ story range? So the one I showed at the beginning from the project that was called LA Live, I believe was 52 or 56 story. I can't remember. I have to put the slide back on again. So that is the tallest that I'm aware of in the North American market. I believe they went a little bit taller than that in China on the steel plate shear wall in recent years. So I've got that information on the Chinese one. I don't know it at the tip of my tongue, but that's something we're in the process of putting for the next edition of the design guide. We'll have that one in there. Let's see. Is the weld continuous? So there's a, let me say it. I think at the University of Alberta, they tried a number of different ways to weld the plate to the boundary frame. And all of them had continuous welds, I believe. And all of them worked well. So what I've done in the textbook is I've showed all of the ones that they tested, and they all worked okay. I have tested and I have seen built in the field some steel plate shear walls with bolted connections, right? So you can do it with bolted connections. And you have to be careful not to end up with a net section failure, right? And I always call that a postage stamp failure, but I realize I'm dating myself now because postage stamps nowadays are glued on, right? There's no more these little holes all around that you would have if you think of a steel plate with bolts all around. But it's been done. We tested one in the lab and it worked. So it's just a matter of making sure that you will not have net section failure before full yielding of your plate, right? And if you do that, it's certainly fine. But the question of discontinuous weld is a good one. I have never tried or tested a discontinuous weld because in the back of my mind, it worries me a little bit to have all these discontinuities along the length. I can't say it's right or wrong, but I personally, if I was to do a steel plate shear wall, I'd weld it all the way in, so there's no discontinuity in my weld. Question, page 86, 85. I don't know what page, probably a slide number, right?
Yeah, that's a question I get from people.
So multi-tiers. So the technically, these walls are very strong. I mean, you take a diagonal brace in a concentrically braced frame, and if it's an inch square, say, of steel, it's pretty small, I'm making a number, and you spread it over the entire length as a plate, you end up with a very, very thin plate. So these walls are quite strong. So the reason why you have multi-tiers, I guess, is you must have an enormous load, or it looks like it's a multi-tier, but it's not. It's just a panel in which they needed to do a door. And to put a door, you cannot just cut the plate and leave it like that. You have to reinforce it with 2 columns next to the door and 1 beam above the door. And that's why they are called boundary elements in the US standard as opposed to beams and columns, because some people felt, well, a beam has to resist gravity load, a column has to resist gravity load. and these are just framing elements around an opening. And so we're going to call those boundary elements. And so you may see a steel plate shear wall that has a certain width, and it may sound like it's 2 panels because there's a door in the middle, but it's just that they need this width and they needed to put a door as well. I don't know if that answers your question, but
Yeah, I guess so.
that's the idea. Now, one thing you could do though, and I've seen people do that, and it's been studied by others, not me, is to have 2 steel plate shear wall and coupling beams in between. And that has an advantage a little bit. It gives you smaller interior columns if you do the free body diagram of that plastic mechanism. That can be an advantage or not. You sort of have to work out the numbers. Let's see. I think I've answered everything here, have I?
The other question, there's one more question. What basis do we decide to use SP steel plate shear wall over a concrete shear wall?
It's a good question. A steel plate shear wall, in my opinion, will provide energy dissipation at every level along the height. So you're spreading the demand over the height of the building. I've always thought of that as a good thing. In a concrete shear wall, you will probably have a flexural hinge at the base. Do you prefer that? I think as an engineer, you have a choice. You're at liberty to pick the structural system that you think will perform better. Repairability wise, I know a lot of folks don't think about earthquake repairability because they say, oh, if it happens, we'll deal with it back then. I think it's a lot easier to deal with repairing a steel plate shear wall. You just take the plate out, put a new one, than repairing a concrete wall where you have to sort of take every bar out of the wall, plus some development length, put new bars. And we've seen the consequence of that after the Christchurch earthquake. And if you're not familiar with the Christchurch earthquake and its consequences, I would direct you to my website where I have a link to a report in which we studied the rebuilding of Christchurch following the 2011 earthquakes there that happened. And one of the points that's interesting is that in Christchurch, most new buildings constructed were reinforced concrete buildings prior to the earthquake. I mean, it's the state of practice, the influence of Park and Poly, I guess, and there's a lot of good things that led to that decision. People were familiar, and when you're familiar with something, you sort of keep doing what you're familiar with. When the earthquake happened, only 2 old buildings collapsed. We heard a lot about those in the news, but very few people heard about the fact that there were hundreds of reinforced concrete buildings that had damage that did not collapse. So if you look at the intent of the code, that buildings should not collapse, they met the intent of the code. But the owners were stuck with buildings that had damage that to repair them, okay, so you have a plastic hinge on the beam, you have to scrape away the concrete, replace the rebar. Oops, it needs some development length in the beam and in the columns. You have to take away some of the concrete in the column. To do that, you have to shore the floors. That starts to be expensive. So they essentially said, let's tear it down and build a new one. They'll be cheaper. And they rebuilt in steel. And that was quite a phenomenal observation to see that a city where pretty much every new building was concrete, all of a sudden was rebuilding in steel. And most of the engineers just did their homework, learned about steel design. And that report that you can download from my website, I can't remember exactly where the link is, but it says Christchurch Reconstruction. It's a publication in New Zealand that I worked with Greg McRae, where we essentially interviewed not all, but the 10 largest engineering firm in Christchurch that were building new buildings. And we asked for every building that they did as part of the reconstruction. What structural system was there? Why did they pick this structural system? And we sort of collected this massive data there. And it was very interesting to see that steel was by far going to be the material for reconstruction in Christchurch. So when you ask me what to do with steel and concrete, I've got many reasons why I would go for steel myself. But again, it's a matter of preference. Who am I to tell you what to do? Okay, so range of steel plate thickness. I don't know what the range of steel plate thickness is. I guess it can go up pretty fast. If you got a 50-story building, I wouldn't be surprised if it's half an inch thick. If you have a 4 or 5-story building, you're probably going to be at the low range of what's available as a hot rolled steel, and you're going to use perforation to weaken it some more, because even there you'll have too much strength, right? So that's when the perforated steel plate shear wall came about. And then what would be the thickness that you would need depends on which your seismic region is and what are your seismic loads. When I was in practice in Toronto, we had a building in Ottawa, which was a warehouse, and the seismic loads were so huge because of all the weight that was there. When we designed the walls, nobody believed we needed that many walls in that building. They all thought we were crazy. Then they checked the numbers and says, yep, that's what we need. So every building is different. So I can't give you a general rule of number of thickness per number of stories. That doesn't exist. But we've seen half an inch in practice. We've seen the lowest hot rolled, and we've seen cold rolled walls as well. The buildings in Montreal that I've shown you, I think, are cold rolled steel, and so gives you a range. FBD. Okay, thank you very much. My question: can we rely on
Free body
diagram procedures for resilient design of steel plate shear wall system? What is the gap needed to be addressed from point of view of design guidelines? I'm not 100% sure what you're asking me there, honestly.
Oh,
force-based design.
Force-based
design. Okay, for resilient design. I'm not sure what exactly you're driving at there still. That might be a longer discussion than what we can just do in WebEx. Okay. Yeah. What are the things that still need to be discovered in this field of steel plate shear walls? Interesting. I honestly don't think there is a huge amount of stuff, but one thing I never do is give you my research IDs ahead of time. Because it's part of the process to come up with good research topics. So if I had a good one, I wouldn't tell you. But honestly, I think there's a lot of mileage that has been done in recent years on steel plate shear walls. So I'll leave it to you to tell me what you think is still needs to be done. Let's put it this way.
Okay, great. Thank you, Michel. Thank you once again, and for your time and for those very insightful presentation and opinion.
Hello.
Oh, somebody's there.
Yeah.
Thank you, Professor. My question is that the guideline you showed, like the R value and the overstrength factors, are for force-based design procedures, right? And then you also showed us that it could be a damage avoidant kind of construction. So my question is, how sure are we that the current design guideline would assure us to have the intended performance level, or do we need to do more work? What's the state of the art from the design guideline point of view?
Well, again, that's a pretty open-ended question, because any structural system will probably have the same issue, right? If you do an R-factor design, you get what an R-factor design gives you. Nothing prevents you from doing nonlinear inelastic analysis if you want to get more knowledge and you want to question what would be the outcome of your design for various scenarios, right? And for some building heights, you might have no choice but to do that. You might be required by code. So I don't think I have a blanket statement or answer to your question. I think the answer is it depends, right? but there's nothing inherently wrong with the existing provisions. They're just as good as every other provision for the seismic performance of structures designed by these methods, right?
Okay, thank you.
Yeah, if you're asking me what's the residual drift, I can't tell you what's the residual drift. You have to run nonlinear analyses on your specific design and see, right? And this will be conditioned by the accuracy of their nonlinear models. I've been advocating for years that anybody who does a nonlinear analysis as part of a design should probably be peer reviewed, because there's so many things that could go wrong in nonlinear analysis. And I'm sure you've seen some yourself, that it's good to have a second set of eyes looking over and reviewing a nonlinear analysis project. And that's happening in the United States for many projects where they have serious limitations in the codes in terms of height limits. So as soon as they exceed those height limits, there's peer review automatically involved, and they end up doing non